Hey there, Pat. Having trouble finding the area under that bridge?
Who are you?
What bridge, you ask?
What are you talking about?
Why, I mean that bridge right there.
How are you doing this?
How are you going to go about finding the area, Pat? You weren't planning on measuring the area inch by inch, were you?
What is even happening right now?
Well, Pat, it looks to me like you need a lesson in Riemann Sums. Would you like me to teach you?
What?
Yes.
Excellent. Let's begin our adventure.
No.
Riemann Sums is a tool in calculus created by a German mathematician named Bernhard Riemann in the mid-1800s. Riemann was especially influential in the field of developing calculus and has gifted the world many lasting contributions in the world of analytics, number theory, and differential geometry. One day, Riemann was sitting around and he thought, "Gee, it sure is strange that there isn't any fast way to find the area under a curve." So after this thought, Riemann thought long and hard about how he could fix this dilemma, until eventually he got it. He could easily find the area under a curve. However, he could easily find the area of a rectangle. By making multiple rectangles within the curve bounded by the x-axis, Riemann could add up the sum of all of the rectangles in order to find the approximate area of a curve.
We found the equation of your bridge, and it's going to be represented by the function negative x squared plus 9. We're going to use an interval of 0 to 3, including those numbers, so we're going to use brackets, and we're going to use 6 rectangles. To find the height of each rectangle, you're going to use a simple equation where you just find the difference between the two endpoints of our interval and divide it by the number of rectangles. So now we're just going to draw a graph, and since the height of all of our rectangles is going to be 1/2, we're going to have to draw in our half intervals there. So this is half of your bridge, Pat.
Oh, thanks.
So now we just have to go up from the right side of every rectangle until you hit the curve, and then draw a straight line across until you hit the other line. And when you do this, you're going to count and make sure that you have 6 rectangles. And because the rectangle for when the function equals 3 would just be 0, because the function value of 3 is 0, there's not going to be a rectangle there. So the area of that rectangle is just going to be 0, but we're still going to add that in as an endpoint. So for this equation, we have to take the base, or the height of each rectangle, which is 1/2, and since we're going to be multiplying that by every one of the function values, we can just take it out front. Then add up the area of all of the rectangles, and then we're going to come up with an approximate area of...
Drum roll, please.
15.625 units squared, and because it's area, we have to have that squared on.
Okay, Pat, so now we're going to do the same thing, but we have 6 left end point rectangles instead. And to get delta x, you're going to take 3 from your interval, and you're going to subtract 0, and then you're dividing by 6, which is from the 6 rectangles. And you get delta x equals 1/2. So then you're just going to draw in 1/2, like you're going to go by 1/2 on the scale, and go all the way up to 3, which is your the end of the interval. And then draw in your bridge.
Half a bridge.
So yeah, you go up from the left and all the way up to the curve, make your point there, go over to the right, and go back down. And you keep doing that till you have 6 rectangles. Okay. So for the sum, you have to multiply 1/2, which is delta x, by f of 0, f of 1/2, and you just keep going all along. And to get the values that go in there, you just go back to your original equation, 9 minus x squared, and you plug in the value. So to get 9 right there, I just went back to 9 minus x squared and I plugged in 0, and that's how I got that.
Fast forward through this. Fast forward through this.
So then in the end here, we have the sum as 20.125 units squared. There you go, Pat.
Alright guys, so I think I'm ready to try this now. So we have the equation of the bridge, 6 rectangles, the 0 to 3 intervals. So I'm going to start out with finding delta x, and I believe from the past examples you find that by subtracting the 0 from 3 and then dividing it by the amount of rectangles, and we get 1/2, which is going to be the interval by which we travel. So on the graph I'm going to set that up so that we have 1/2 bases, or height, I guess, as some people call it. I don't know, it's pretty weird. It's a base, I mean, whatever. So I'm going to go ahead and I'm going to draw my graph right now. There's my really good curve. It's probably the best curve anyone's drawn yet. And what you do with midpoint, so I've heard from a rumor, is that you go up the middle of the interval, so in between 0 and 1/2. So that's going to be 1/4. And then you keep doing that. You stop at the curve and you go in each direction until you hit the other curve or until you hit the next interval. And you're going to keep doing this. And these are going to end up being the rectangles that you're taking the area of, and then you're going to be adding up to find the total of the curve under the curve as a whole. So here I go with finishing that up. Now I'm going to move on to finding the sum. So s equals 1/2, because 1/2 is the interval by which we're traveling. And then you're going to do the equation of 1/4 as 1/4, as I said. Fix it. There we go. Alright, I fixed it. So we're going by the area between the intervals because it's mid. So just going to keep writing these down one by one, you know. It's a slow process, but I think in the end, you're really thankful that you stuck with it, because it's really worth it in the end to have gone through this process and know that you've come out the other side, you know, a better person. I think mathematicians are probably the best people. They're the kindest people. Anyways, so we have that all done now. And so now that we have that set up, we can write down the actual numbers within this. So I'm going to go ahead and do that. Interesting story. We're just going to fast forward through this. Alright, so we've gotten all these now, and we're going to write down the real numbers, which actually, you know, the actual areas of those rectangles, and this is where the real addition comes in. So as soon as my hand starts moving, I will, okay, so we've got these going for us. We got 8.937, it's a good number, and then we got 8.437, it's a little bit bigger. That can be expected, or it's a little bit smaller, actually.
I just started today. You can see the areas are getting progressively smaller because the curve is curving downwards and the rectangles themselves are diminishing in size, just as my patience is with this project. And
Alright, so here we have the numbers, and the video just stopped. So we're going to end up getting the answer of 18.061 units squared. And this is an acceptable answer because we're not going to get the exact answer because, like, you know, Riemann Sums isn't exact. Like, if you want to do exact, like, go somewhere else. Like, this isn't your party. But yeah, that's about it for Riemann Sums. Yeah. But you still have area above the curve, an area within the curve that's not within the rectangles. There has to be a better way to do this.
Very good question, Pat.
Thanks.
Riemann realized that although this theory works pretty well, it isn't perfect. If you wanted to find the exact area under the curve, you will need to approach the problem in a different manner. This, of course, is when Riemann came up with his next idea, using trapezoids.
Along with getting the area of a rectangle, Riemann also understood how to get the area of a trapezoid. Although more complex, this method would eliminate the problem of overshooting or undershooting the actual area of the curve. So now we have our equation and we have our interval all set, and we've decided that we're going to do 6 trapezoids, so we just need to find the height. So we're going to use delta x, we're going to subtract the interval and put it over the number of trapezoids. And here's our area equation, just so we know what we're adding together. So now we're going to start doing the sum. We got a little ahead of ourselves. We got to go back and draw the trapezoids on the graph. Because all the edges of a trapezoid are straight and the curve is round, the area that we're going to get,
It's in a close approximation.
yeah, the area that we're going to get is going to be just under the actual area of the curve. See, we have all that open space by the last trapezoid, which actually looks more like a triangle. So now we multiplied each of the middle function values by 2, because instead we would have f of 0 plus f of 1/2 plus another f of 1/2 to represent the next trapezoid. So instead we're just going to combine them together and multiply each one by 2, except for the very ones on the end because they're only in the equation once. So now we have to find all of the function values so that we can add them together. Notice how we have 2 1/2s, and that represents in our equation the 1/2 that you would multiply by, and then the height of every trapezoid is 1/2. So instead of writing that over and over again, we're just going to take it and put it out front, multiply those two together, and you're just going to multiply the whole sum by 1/4.
But isn't 1/2 the base?
No, 1/2 is the height. It depends on how you look at it.
Okay.
So at the end we're going to find an approximate area, even though the real area under the curve we found is actually going to be 20. This is a little bit under because we have that extra space because the trapezoid is not round.